Yeah, okay. So hi, everybody. Pleasure to be here this morning. I I spent 4 years at the National Science Foundation working on the quantum information science program and learned a little bit about quantum information here and there along the way. So Vadim asked me to kind of jump in here. I told him I had a canned talk on Peter Shor's algorithm, which is a famous algorithm described in chapter 7 of your textbook. And so this is a talk that I gave some time ago at another institution, and I've kind of changed it around to make it fit this class, and I hope it works for you. So if you have any questions at any time along the way, just jump in and ask questions. It's no problem. If you want to stop me, if there's something you don't understand, please let me know. Okay. Next slide, please. So let's start with something very simple. Let's just start with some classical optics, which may seem like a very strange place to start. But we'll have a light source coming in from the left-hand side. That could be just Newton would have just used the prism to separate out the colors from the sun and used a slit. And we're just illuminating a diffraction grating. And a diffraction grating here is nothing but a transparent thin film that has lines etched in it. So it has a large number of parallel lines etched in it. And the light wave comes in, and as you know, it diffracts off the grating. And this is a perfect example of interference. And you get some interference maxima over on the right-hand side. What I've graphed for you there on the right is just a couple of examples. There's 2-slit diffraction and 5-slit diffraction. The 2-slit diffraction is the red line, which is the small oscillations. The 5-slit diffraction has much more pronounced peak. And if you go and have many slits, thousands of slits, then those peaks become sharper and sharper. And there's an intensity distribution which goes like that function P there. So in the classical limit, you can think of that as just the intensity distribution on a screen that's far away as a function of the angle theta. And that just shows you where the light comes out. So this is just a simple example of interference. If we were to think of this in terms of photons, and quantum particles striking the diffraction grating, then P would represent the probability of a photon coming out in a particular direction. So this is very basic stuff. Let's go to the next slide. So let's start with a quiz. Light of wavelength 441.6 nanometers is normally incident on the diffraction grating. The spacing of the grating is D, and that's the distance between the adjacent lines of the grating. The first order peak, which is shown there in red, emerges at an angle of 7.3 degrees relative to the beam. And what I'd like to know is how many lines per centimeter are etched on the diffraction grating. And so the answer is A, B, C, D, or E. And there's a hint there, so you don't have to do much mathematics in your head. And so what I'd like you to do is just figure out which of those it is and put your answer in as a comment. And that way we can take attendance. I always give a quiz to start a class just to take attendance and make sure everybody's paying attention and everybody's in the room. So Vadim, when you've got enough responses, then we can go ahead.
What's enough?
Okay, next slide, please.
No, what's enough?
When everybody in the room has responded, then we know we can go on. How's that?
Okay. So we've got one response so far. We've got 1, 2, 3, I think 5 students. Not bad out of 14. Okay. So let's do some responses. I guess maybe I should respond to it. Save myself for that.
This is not a high pressure quiz. This is an attendance taker. So.
Should we solicit if anybody needs hints?
Okay, we can go on. I think people felt too much pressure. Here we go. So here's the answer to the quiz. Okay. And the condition for maxima is that d sine theta has to be an integer number of wavelengths. And so you can get d by, and this particular order is m equal 1. So you just take the wavelength, 441.6 nanometers, and you divide it by the sine of 7.3, and which number I gave you in the hint, and you come up with a value for d. And if you take 1 over d, that tells you the number of lines per centimeter. So 2,857 lines per centimeter. Now, you may be wondering why I'm wasting your time with this when really this is supposed to be a lecture on quantum computation. But actually, this is the most important slide in the talk. And so let me try to explain why that is. If we lower the intensity of the incident radiation to the point where just a few photons at a time are coming through the slit, then the photons will appear kind of at random or randomly spread amongst those various blue lines on the right-hand side. So you'll be catching photons, just a few photons at a time as they come out. And I gave you on the previous slide the probability distribution by which the photons emerge. This is kind of a paradigm for computation, and I want you to think about it that way. So let's go to the next slide. So here's something I want you to think about. Assume that we turn down the intensity of the incident light field until we detect individual photons emerging on the right-hand side. Now I'm going to ask you a different question. How many photons would you have to catch in order to determine the spacing, the line spacing d? And at what confidence level? So if you wanted to make a measurement of the line spacing of the grating, and you wanted to do it not using classical light, but using quantum light, then how many photons do you need in order to make that determination? So this is a way of thinking about a lot of what we call the second quantum revolution. In the first quantum revolution, we saw a lot of quantum mechanical effects, but most of the effects that we use in our technology are designed so that they're impervious to quantum fluctuations. If you think about the way transistors work, or if you think about the way circuitry works, or pretty much even laser light, if you think about most of the technologies that we use, even if they depend on quantum phenomena, they're designed in such a way that they're impervious to fluctuations. What we're trying to do in the second quantum revolution is we're trying to use the fluctuations. We're trying to embrace the fluctuations rather than ignore them or eliminate them by redundancy. We're trying to actually embrace them to measure stuff and to get information and to process information as fast as we can. So we're going to come back to this toward the end of the talk after I show you how relevant this whole idea is to Shor's algorithm. So let's go on to the next slide. So we have this situation where in the last 20 years, technology has really been advancing at a very rapid pace. Quantum technology is really amazing. We have people who are isolating individual atoms, addressing those atoms, speaking to those atoms one at a time, and trying to use the quantum interactions, the quantum fluctuations with those atoms in order to process information. The technology is kind of mind-blowing. It's very expensive and involves very high-tech instrumentation. Much of it is done at national labs like the National Institute for Standard Technology, and it involves probably the most state-of-the-art developments in physics in the current era. So all of this technology is designed to make use of those fluctuations. And so let's go on to the next slide here, because I want to try something a little bit different. Here's another simple example of, and I like to use this example because it helps to think about these things. This was an example from my daughter, actually, when my older daughter came home from middle school class many years ago. And she was very excited because her teacher used to start every class with a riddle, just like I start every class with a quiz. And so here's a very simple riddle. And I remember this one in particular, I remember she was very proud that she solved this riddle. A man in a suit is found dead in a puddle of water in a forest. Don't be sad, it's just a riddle. So the rule of the game is that you're supposed to ask me yes or no questions. So all you can do is ask me a question that I can only answer with a yes or a no. And the object of the game is to ask as few questions as possible to figure out how the man died. Kind of like catching as few photons as possible to figure out what the spacing is on the slit. My daughter was very proud this particular day because she had managed to solve this riddle with only 5 questions. If you go to the next slide, you'll see what those 5 questions are. The first question she asked was the suit a business suit? And the answer was no. So then she asked, was it a swimming suit? And the answer was yes. Was the puddle made of rainwater? And the answer was no. Was the water dropped from a helicopter? The answer was yes. And so was the man accidentally scooped from the sea while swimming and dropped onto a forest fire? And the answer was yes. And so she figured out the riddle with just 5 questions. And so, we think of yes or no questions as being very blunt instruments in some respects. They're not as subtle as most human communication. When I talk, I'm Italian, I use my hands a lot. I use a lot of gestures, metaphors, similes, body language, all kinds of different aspects of my speech and my way of communicating information to you. Yes or no questions are kind of tricky because you really have to focus your efforts and ask questions very precisely, and they give you very precise answers. And so the whole issue of how we extract information and how we communicate information has a long history in science. It really began with George Boole back 200 years ago, who figured out what he called at that time the laws of thought. Now, people since that time have changed their view about what he really did. They really think of him as the founder of algebraic logic. Claude Shannon, who was really the founder of information science, modern information science, really picked up on Boole's work to figure out a mathematical theory of communication. And Alan Turing really studied Shannon's work in order to figure out and to think about how information is processed in machines, and he came up with the automatic computing engine. John von Neumann and John Bell were both colleagues of Alan Turing, and they worked on physics, and they were interested in the physical aspects of Turing's idea of information processing. Von Neumann in particular worked on the mathematical foundations of quantum mechanics, and he was really the first one to understand information in the context of quantum systems. Eventually, von Neumann's ideas really could be used to rule out, for example, hidden variable theories in quantum mechanics. And so eventually Bell developed his famous inequalities in order to better characterize von Neumann's understanding of information. And eventually Alan Aspect tested Bell's theorem in order to rule out hidden variable theories in quantum mechanics. So it really was always about embracing the fluctuations and figuring out how random fluctuations in nature can be used to convey information. So there's a long history here that predates the science of quantum information science that's described in your textbook. We're going to get back to this issue again by the end of the talk also. So let's go on to the next slide, and let's get really to the subject of the talk, which is this guy here, Peter Shor. In 1994, Peter Shor demonstrated that if we could build a quantum computer, whatever that is, then we could use it to factorize large integers. And we can do that far faster than you could do it on a conventional computer. And so this single contribution in 1994 really sparked the whole quantum information science revolution. So the problem, simply stated, is that if you have a large integer n that's formed by multiplying a pair of prime numbers, can you, if you're given the value of n, can you figure out what the factors are, p and q? And how do you do that? And it's a tricky problem, especially if n gets to be a very large number. Here, n is a number which has something like 1,000 binary digits. Okay, so all we're trying to do is a simple math problem, which is to factor a very large number. Excuse me 1 second while I try to fix my computer here because I'm going on to something else I wanted to do. 1 second. Okay, so that's the goal, and he published 2 papers on that. The first one was in 1994, and the second one was 5 years later. He had to rewrite it 5 years later in a slightly different form so that people could understand it better. But you can see that the number of citations of these 2 articles is enormous, and it's growing every day. It's had a huge impact on physics and science. It's one of these are highly cited papers that really sparked the revolution. In fact, the next slide shows you just how influential these 2 papers were. This is the total number of papers published in quantum computation as a function of time, and it's compiled by Elsevier Press. And you can see that before he published his paper in 1994, there were very, very few papers published in the whole field of quantum information theory and quantum information science, and quantum computation in particular. But then after his paper, there was an exponential growth. So this single contribution had a huge impact on people. Many people jumped into the field and started working on it. And so in some respects, this is the most important chapter of your textbook. It's the one that has in it the seminal contribution which started the whole field. The reason it was important, of course, is because that problem of factoring large integers figures into cryptography, and it figures into the way that we protect information in computer systems. The difficulty, the amount of time that it takes to find the factors of a large number is a key element for how one uses cryptography to protect information in computer systems. Your book describes that a little bit more. I won't go into the detail. We're going to take it as a pure mathematical problem and see what we can do with it. So let's go on to the next slide. Okay, so the problem of fast prime factorization, Shor's problem of factorizing a large integer, can be reduced to a problem of period finding. A little bit like the problem of finding the distance between lines in a diffraction grating. Okay, we're going to be trying to find to solve a period finding problem in order to do prime factorization. And this idea was really an idea that a fellow named Miller came up with 20 years before Shor published his article. Okay, so let me show you how to do that conversion. It's very easy, simple math trick. And so the next slide just gives you an example, kind of a trivial example. If you have your large integer n, I'm going to choose 7 just to make it simple, and we want to factor it. We can choose an arbitrary integer x and take powers of it. Okay, so in this case, I chose x equal to 3, and I'm going to take powers of 3, and I'm going to do modular arithmetic. So 3 mod 7 is 3, 3 squared is 9, mod 7 is 2, 2 times 3 is 6, 2 times 6 is 18, sorry, 3 times 6 is 18, 18 mod 7 is 4, and you just go like that. And what you find is after the 6th one, you get to the number 1. So, and then after you get to 1, the next time you multiply by 3, you're going to get back to where you started. And so you see that it's a cyclic system, and those numbers, those integers will just keep repeating the more and more powers that you apply. Okay, so we say that the period or the order of 3 mod 7 is 6. And that's just a trivial example. Let's go to the next slide, please. Here's another example. The order of 4 mod 7 is 3. Okay, so let's go to the next slide. And just here's the general proof that it's true for any integers x and n which share no common factors. So if you just take the first n factors of x, that's going to give you n numbers. Now the value of those numbers, because we're doing modular arithmetic, has to lie between 0 and n minus 1. Right? Those are the only possible answers. However, we're going to exclude 0 because if the answer was 0, then x and n would have a common factor, and we're excluding that possibility. So we're assuming x and n have no common factor. So therefore, we have n integers picked from a set of n minus 1 objects. At least 2 of them have to be equal. And if 2 of them have to be equal, then the sequence has to be periodic. And this is just a demonstration of that, okay? So we're gonna use if you look at the bullets at the bottom, the smallest integer r for which x to the r mod n equals 1 is called the order or the period of the sequence, okay? So what we're gonna be doing is looking for r. All right, next slide. Okay, that's just a summary of what I just said. X to the j mod n is a periodic function, and the period of the function is r. Given x and n, how do we find the period? That's the whole question we're trying to figure out, okay? Now, I'm going to show you in a minute why that allows us to find a factor of n, but for now, you just need to know that it's periodic, and we're trying to find the period. The most straightforward way to evaluate the function to do this is to evaluate the function for different values of j until you find the smallest j for which x to the j mod n is equal to 1. But if n is a huge number, if it's got 1,000 binary digits, then this is a very computationally very time-consuming process. So let's go on to the next slide. Here's another example here, and I'm going to use this example a lot. 7 to the j mod n, and I just plotted it for the first 155 values of j, and you can see that it's periodic, and you can see that the first time that you get a value of 1, then that's at j equal 4, which is the period of this particular sequence. Okay, next slide. So why is this important for finding factors of n? Well, if x to the r mod n is equal to 1, and if r happens to be an even integer, then you can do a little trick here, like completing the square. X to the r over 2 times x to the r over 2 mod n is equal to 1. You can rewrite that as x to the r over 2 minus 1 times x to the r over 2 plus 1 mod n equal to 0. And therefore, either of those factors must have a common factor with n. Okay, so we have multiplying 2 numbers, taking a mod n. If we get 0, that means that one of those 2 things has to have a common factor with n. So we found a way of finding a factor of n. So we're using periodicity to find a factor of n. So that means that the first step of Shor's algorithm is really a classical piece. If we're given a large number n, we choose an x at random. We find the order r of the sequence x to the r mod n. If r is odd, we can't use that information, so we go back and we try another value of x. But if r is even, then we can calculate r over 2, and we can evaluate x to the r over 2 plus or minus 1, and one of those has to have a factor in common with n, and we've solved the problem. Now, the hardest part in this sequence of events is to calculate the order of the sequence, okay? That's step 2. And that's what Shor's algorithm is designed to do. It's designed to find an efficient, fast, effective way of finding the order in this particular sequence of integers. It's a purely mathematical problem, but it's not unlike the problem of finding the distance between adjacent lines in a diffraction grating. we're going to do some spectroscopy here in order to figure out the period of the sequence. So next slide. Well, there's more than one way to skin a cat, and there's more than one way to find the period of a periodic function. Okay, all right, next slide, please. Another way of finding the period of a periodic function, I'm sure you're very familiar with, you just take a Fourier transform of the function. So down the bottom there, I show you this function g of k, which is a discrete transform of the function y of j, which is the periodic function whose period we're trying to determine. And on the right-hand side, I show a graph of the absolute value of g of k squared, and you see that there's 4 peaks, one at 0, one at 39, and then 2 higher peaks at integer multiples of 39. So if we can somehow just take a Fourier transform of the function and identify the position of the first peak, then R over n is m, where m is the range of x, 155 in this case, divided by the position of the peak, which was 39, and that comes out to be 4, and that shows us that r equal 4 is the period of this particular function. So from the Fourier transform, we can determine the period. Next slide. And this is just showing that indeed 7 to the 4th power is 1. When you do the arithmetic mod 15, excuse me. Next slide. And then 4 divided by 2 is 2. So 7 squared minus 1 times 7 squared plus 1, which is 48 times 50, mod 15. And that's the same as 2 to the 5th times 3 to the 1st times 5 squared mod 15. And so you see the factors of 15 pop up right there in the factors of 3 and 5. Okay, so this is how you do Shor's algorithm. It's really very simple. You just have to find the period of the function. Okay. Are there any questions? Everybody got it? It's a simple math problem. We're just trying to find the period of a function. That's all we're trying to do. Okay, if there's no questions, let's go on to the next slide. So Peter Shor was thinking about this 25 years ago or more, and he asked, what kind of a gadget could we build that would input 2 numbers, x and n, and output the Fourier transform signal, and would do it very fast for very large n, for n's that had thousands of binary digits, because this is the key to the encryption algorithms that are used in modern computation. All right, next slide. And here's his answer. And the answer's in your textbook. I'm not going to go over these slides in detail. There's a classical part, which I already went over with you, which reduces the difficult piece is the order finding subroutine. Okay, so that's just what I was telling you about a minute ago. And there's a quantum part which tells you how to actually find the order. It's the order finding subroutine. Okay, and you can see that it's just a 6-line algorithm, and that it uses a couple of quantum registers. In line 1 on the right hand side, there's 2 registers. One is in the state 0, and another is in the state 1. And then there's some transformations that he's doing on the registers. So we're going to go through those in detail. We're going to try to understand all the steps in the process. But it's really a very simple algorithm. And the output of the algorithm at the bottom is R, the period of the function. Okay. What you can see is that in line 3, there is a superposition of the states of the 2 registers, which gives the function we were talking about a minute ago. J is the x-axis; it's an integer along the x-axis, and x to the j mod n is the function that was the periodic function that I plotted in my previous graphs. So he's just somehow writing this information onto the quantum states of some physical system in order to determine the period R. Okay. All right, let's go to the next slide. Graphically, Shor's algorithm looks like this. There's three parts. There's a bunch of H's on the left, which you'll probably recognize by now as Hadamard gates. There's some unitary transformations that take place in the middle with all those U functions. And then there's an inverse quantum Fourier transform at the end and readout of the state. So there's three basic parts of Shor's algorithm. And we'll go over each step of that and see if we can understand why it's being done the way it is and what it means. Next slide, please. My favorite qubits, doesn't really matter what qubit we use, but I like to use these. My preferred qubits are ions in a linear ion trap. So each of these things is an atom or an ion. In this particular case, an ion. And so we have a little abacus here, which is composed of individual atomic particles. And in particular, we're assuming that each of those particles is a two-state system. So it may have a spin, a quantum spin, which can have either a spin up or a spin down. So it's a two-state system. Or it may be that each ion has two energy levels that are slightly separated in energy. So it's a two-state system, and the ion can be in the ground state or in the excited state. But those are the only two states in the system. So it can either be a spin system or a two-level atomic system. And having a string of those things together, that's going to be the abacus on which we do Shor's calculations. Next slide, please. So before we do anything else, before we go on and talk about how we're actually going to do the computation, I want you to think a little bit about how we encode the information in that function shown up in the upper right-hand corner onto these quantum registers. And so the registers are actually composed of a set of bits. So on the left-hand side, I showed you that it takes about 3,072 classical bits to record that function on the upper right-hand corner. The blue bits, the blue classical bits, give you the binary representation of the J value along the x-axis. And the red bits are going to encode the information along the y-axis. We're going to take a large number of values of J so that we have many periods in our function so that we can take the Fourier transform. And the rule of thumb is that J is going to go from 0 up to some large integer m minus 1, where m is of the order of 2, in this case, 2 to the 8th, it's 256. But the key is that it should be something like n squared. Now, in our case, n is 15, n squared is 225. So we're going to choose m to be 2 to the 8th power. We have 256 values of J. That gives us enough oscillations that we can easily resolve the period from the Fourier transform. So that value of m is what I want you to keep in your head here. In this case, it's 2 to the 8th. That means we need 8 classical registers in the blue boxes on the left-hand side to encode that information. Now, the value of y is somewhere between 0 and n minus 1, n is 15. So we're doing modular arithmetic. So y goes from 1 to 14. So therefore, we're going to need about 4 classical bits to represent that information, 2 to the 4th power, 16, okay? So the sizes of the registers matter. Classically, in order to represent that picture in the upper right-hand corner, for every J value, we need a Y value, okay? That gives you the map of the function. And we have 256 of those classical registers in order to encode that entire function on the right-hand side. In the quantum system, we're going to replace those 12 classical bits times 256 with just a single string of 12 quantum bits or qubits. And so this looks like a great savings, right? We're going from 3,072 classical bits to describe that function to only 12 quantum bits to describe the same function. And the reason we can do that is because the state of those 12 quantum bits is going to be a state determined by an interference phenomenon. And so there's going to be a superposition of all of the states, of all of those states. In other words, those 12 quantum bits can exist in any one of the rows on the left-hand column. Okay, so at any given time, if you were to measure, say, the z component of the spin, and I'm assuming that, you know, spin up is a 0 and spin down is a 1. Okay, so if we measure the z component of the spin of those 12 objects, we would just find a certain set of values of zeros and ones in our quantum system, and that would correspond to one particular line out of those 256 lines on the left-hand side. Okay, so we just get one data point. Of course, we'd have to repeat the measurement many, many, many times if we were actually to trace out the whole function. So it's not quite clear that we've saved anything in going from the classical system to the quantum system, because anytime we do a measurement, we lose all of that information that's contained in the superposition. Next slide, please. So you can think of this as kind of a Monte Carlo kind of thing. If you just roll the dice and you measure all those quantum bits on the right-hand side, you're going to get one value. Next slide, please. Or some other value. So you're going to pick out one register or the other, depending upon what you happen to measure at any given time. And last slide, please. Next slide, please. So any random selection, right? So any random measurement that we make of our 12 quantum registers is just going to reproduce one of those things on the left-hand side. I don't know why I took 3 slides to say that simple thing, but I did. But the key here is that in a Monte Carlo sense, if you really wanted to map out for yourself that whole periodic function, you'd have to perform the measurement this way many, many, many times on the quantum system. And so you really haven't saved anything over the classical system. There's no savings associated with this, right? Okay, so how are we going to actually save time and do things quickly? Next slide, please. Well, that has to do with our quantum bits. Okay, our bits can be measured along the z-axis. If we do that, then spin up along the z-axis corresponds to the state 0. Spin down along the z-axis corresponds to the state 1. But we can also measure that spin along any direction that we choose. We don't have to measure the quantum bits along the z-axis. We can measure them along any axis that we please. If we were to measure them along the positive x-axis, that's shown here going off to the southwest, if we measure along the x-axis, a spin-up state is a superposition of the states spin up and spin down, 0 and 1. And that means that if we prepare an atom with spin up along the z direction, and then we measure it along the positive x direction, we will either get up or down with probability 1/2. We get random results with probability 1/2. We could also measure along the y direction, which corresponds to different superpositions of those two states. So this property of our quantum bits this is basically the essential quantum mechanics of a qubit, and it's showing us the quantum weirdness associated with making measurements using fluctuations. So next slide, please. So let's go ahead now and start with Shor's algorithm. If you've been sleeping till now is the time to wake up, okay? Because here we are, and we're going to start Shor's algorithm. And we're going to start over on the left-hand side by preparing our quantum registers. Next slide. So we're going to set the table. We're going to prepare the J register. That's the x-axis, okay? Now, I remember we had 8 blue bits, right, or qubits that represent the x-axis. I'm doing it here with 3 just to make it simple so that you can see what's going on. It works the same way with 8, as I'll show you in a moment, okay? So what we're going to do is, instead of starting with our spins along the z, prepared along the z-axis, we're going to start with them prepared along the x-axis, the positive x-axis. So we're going to take 3 spins and we're going to line them up along the positive x-axis. And when we think about that in terms of the z-axis, then each of those spins is a superposition of 0 and 1 along the z-axis. And so you get 0, 1 for the first bit, a superposition of 0 and 1 for the second bit, and a superposition of 0 and 1 for the third bit. And when you multiply all of that out, then you get what's on the second line, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, et cetera, et cetera. And those are what we call in the computational basis that represents the binary digits 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so just having spins along the x, you just take all of your spins and you align them with the x-axis. And if you think about that with respect to the z-axis, then that corresponds to a superposition of all the different number states. And that holds for any number of qubits. So let's go on to the next line, next page. And so it's kind of strange. People think superposition is something kind of strange and hard to get their head around. In this context, it's a triviality. 3 spins along the x-axis, there's no superposition there. As long as you're thinking about the spins along the x-axis, there's no superposition. If you just change the way you think, next slide. If you just change the way you think and you think about those spins in terms of the z-axis, then all of a sudden you have a superposition of states, and that superposition of states is the superposition of number states. So preparing the table is really very simple. We just take all of our spins and we align them with the x-axis. That's all we do. Next slide, please. So this is it. The first register in blue shows 8 spins, all aligned with their spin pointing along the x-axis. And that's equivalent to a superposition of the number states J. Now the Y register, we're going to initiate the Y register by putting it in the state 1. And that's just for convenience. So we have 4 red qubits for the Y register, and we're going to start those qubits in the state 0, 0, 0, 1, which represents the binary digit 1, the binary number 1, okay? And so now we've set the table. That's the first step of Shor's algorithm, is just getting the system into this configuration. Next slide, please. So now we want to move to the meat of the problem, and now we want to hit those bits. So we've taken our spins in our atoms, and we've lined 8 of them up along the x-axis, and we've taken 4 red qubits, we put 3 of them along the z-axis and 1 along the minus z-axis, right? 0, 0, 0, 1, right? So 3 of them were along the positive z-axis and 1 was along the negative z-axis. And so we've got them all set up now, and now we're going to do something to those spins. We're going to hit them with some unitary transformations. That means a physical process or a set of physical processes. We're going to drive them somehow into the states that we want, into the superposition of states that we want to manufacture. Another way of saying that is that we want to write our periodic function onto this medium of these spins. That's what we're trying to do. We're just trying to write the periodic function onto the spins. Let me try something for 1 second here. I'm preparing myself for a part of the talk that I can't get to any other way. So I have to get my other computer up and running. Okay, so we've set the table. Now we have to do the work. So let's go on to the next slide. Now we have to prepare the food, okay? And the first line is what I told you a minute ago. This is how we set the table. The second line tells us that we're going to use some unitary transformation. We're going to construct some Hamiltonian. We're going to interact those ions with one another in some complicated way. We're going to drive them into the states we want. We're going to write this function 7 to the j mod 15 into the Y register. okay? And that's a highly non-trivial thing to do. It's non-trivial even classically. If you think in your head, okay, how am I going to calculate 7 to the 4th mod 15? You realize you do a lot of gymnastics in working out that number, right? Okay, you do a lot of mental gymnastics in order to do that. You have to somehow take 7 to the 4th power in your head. That involves some multiplications. You have to do modular arithmetic, which involves some division and some truncation or something like that, right? You have to figure out a lot of those processes. And in addition, you have to have workspace in your head to do all of that, right? So you have to have some extra bits lying around somewhere where you can put the intermediate results of your calculation as you go, right? So there's a lot of work that goes into writing this information down and actually doing the computation. Step 2 is the actual computation we have to do somehow. We have to get those atoms in our array to and put them into this superposition that we desire. Okay, that's what we have to do. Hold on one second. Let's see. Okay. So let's think about a little bit about what this operator U has to look like. Okay. Well, I'm going to write U as another operator A to the jth power. And the reason I'm going to write it this way is because I don't want to do anything to the X register or to the J register, right? In other words, when I apply U to this function, I don't want to change my spins along the J axis, okay? I've set them up exactly the way I want. They represent the numbers 1 to 255, 256. I don't want to mess with those at all. So that means that this operator J here, so it's A operator to the J operator, operator J has to commute with A, okay? It's not going to mess up. A is not going to change the quantum state of the X register. It's only going to operate on the spins in the Y register, okay? All right? It has to, I mean, that's a key feature. It has to commute with the spins along representing the J register. What is the operator A? Well, A has to change the state Y to 7 times Y mod 15, okay? And if we do that J times, we get 7 to the J Y mod 15, and that's what we're trying to do here. So that's why we prepared the initial state in the value 1, because if Y is equal to 1, then A to the J times 1 gives me 7 to the J mod 15. That's the function, the periodic function we're trying to generate, okay? So this is just really explaining my notation. There's nothing here except notation, okay? But we have to be very careful about this. And here I just wanted to emphasize something that, and when you're reading your textbook, you can easily get confused if you're not careful. You have to beware of the extra states, okay? And this is a simple thing. 7 to the J mod 15 is going to be a number between 0 and 14. So there's 15 possible values for this register. However, we're representing this register by 4 qubits. That means we have 2 to the 4th, which is 16 possible states, right? So there's 16 possible states of those 4 qubits, but we only need 15 of them to represent our Hilbert space here. So that means if we're not careful, we could be driving some of the population of our atoms into a state where all the spins are down. That's the state 1111, okay? That corresponds to the number 15. And we're doing a modular arithmetic. Our answers can only be between 0 and 14, okay? So there is a state which is actually not supposed to be part of our Hilbert space, but it's in our qubits. And if we accidentally drive population into that state, then we're in trouble, Okay, so there's a, you know, representing representing this particular register by qubits has an intrinsic problem with it, which is that there's extra states. And for the case of you know, n equal 15, it's not a big deal. There's just one extra state. But if we go to very large n's, there are going to be a lot of extra states lying around that we really don't want as part of our Hilbert space. And that means that when we do our operations, we have to be very, very careful. It creates a lot of difficulties. We can't always assume completeness and things of that kind. So you have to be careful even when writing down your theorems and whatnot, because you can easily make mistakes if you're not recognizing that you're projecting or that you're doing your computations in a Hilbert space, which is really a subspace of your physical Hilbert space, which is the space of the four quantum spins. Okay, so you have to be very careful about that. And so, so this is our operator U. The J basis is written here in terms of base 2. So these values of J1, J2 to J8, those are either zeros or ones, okay? These are the Z components of the spins, if you will, written as zeros and ones, and they represent the numerical value of J. And so when we calculate the 7 to the J mod 15, we're going to be applying A to the J, where J is written as this decomposition, and then it breaks down into this set of matrices here, okay? And all of this is described in one paragraph in your textbook, where they're trying to tell you how to compute this guy, okay? And they tell you that, so remember, each of the J's is either a 0 or a 1. So this is either 1, in which case it does nothing to the state, or it's A. So you're going to have an A here, an A squared, an A to the 4th, an A to the 8th, an A to the 16th, an A to the 32nd, right? You're going to have powers of A here, and you're going to have to compute those matrices in order to do this. So this all looks very nice and pretty mathematically. The reason I'm trying to log on here is because I want to show you what it looks like in practice. So I'm going to show you here what your book doesn't tell you. Now I got my computer working again. So hold on one second. Vadim, I'm going to try to log in again from my other computer. Okay?
Sure, just let me know when you want to stop sharing.
Here we are. Join the audio. Okay, can you stop sharing? Let me kill this guy.
This guy, yeah. The other one is muted, Mike.
Good. Here we are. Now I'll share my screen. This is what they don't tell you in your textbook. Okay. This is a paper that actually shows you how you do the modular exponentiation. Okay. X to the J. This one was published in 2014. And I want you to get just a feeling for what's involved. That picture should look familiar to you. That's Shor's algorithm. Okay, that one doesn't look too much different. Now that's starting to look a little funnier. I just want to show you the pictures for what's involved in constructing such an algorithm. Now we have something called adders. So they're constructing computational quantum adders.
This is a controlled adder. Doubly controlled adder. Generic adder. Multipliers. Initial multiplier accumulator. 3-qubit gate decomposition. I can go on and on and on. It's a very long article. Here we go. Here we get to some fun looking diagrams here. Okay, I'm trying to give you an impression. That's all I'm trying to do. Okay, I want you to get an impression about what it takes. Okay, here we go. That's part 1 of the answer. Okay, there's part 2 of the answer. Okay, all right. Okay. I just wanted you to have that picture in your head. I'm not gonna share it anymore. Now we can go back to the slides where we were. If you can do that easily.
Okay, just a minute. Where are the slides?
Or I can put it on mine if you'd rather now. So either way. Okay.
It's up to you.
Okay. So let's see.
I think that's what.
Yeah. So you see, actually implementing this U is a very complicated business. Okay. Actually writing the information in this periodic form, that there are simpler ones than the one I showed you. The one I showed you is the fastest one to date. But even the simplest ones are quite complicated. Like I say, if you do this operation classically in your head, it's also very complicated just to do it. And here what you're trying to do in these quantum algorithms is you're trying to write them in terms of universal reversible quantum gates. And in order to do that, you have to really do a lot of subtle operations. It's a very complicated business. But what's really surprising about it is that in 1994, Shor figured all this out long before he'd ever written down an algorithm. I mean, your textbook wasn't written in 1994. There wasn't any textbooks on this subject in 1994. None of the things that you're learning about were known in 1994. All he knew was what he invented himself and some very general theorems by Bennett and a few other people on the existence of universal quantum gates. So remember, all of this is supposed to be executed on a kind of universal quantum computer which utilizes universal gates, which can compute anything. So what Shor assumed in writing his paper was that to calculate this 7 to the j mod 15, he could essentially use the classical algorithm for calculating that modular exponential. The only thing he had to do was use the classical algorithm for reversible classical gates. Most classical gates are not reversible, but you can do classical computation in terms of reversible gates. So he had to imagine that he was going to use reversible classical gates and then mimic those with the quantum computation, because quantum gates are intrinsically reversible. So, and really he didn't even need to do that, because he was just trying to figure out the space and time resources that would be necessary to do the computation. He didn't actually have to write the algorithm down himself, and he didn't do that. It's all kind of strange. Let's go down to the next slide.
Can I just, I want to make sure I understand the point that you're trying to.
Sure.
When we were discussing much simpler sort of elementary algorithms like Deutsch and Deutsch-Jozsa, in the book, I believe I forget where I picked it up, but yeah, I think it's also discussed in the book that there's an assumption that the oracles that you're trying to learn something about do not produce exponential overheads or they're not difficult. You know, basically we're assuming that we're given this black box to encode the states with, we don't worry about, oh, what if this black box is impossible to implement? Is this what you're talking about?
This is
No.
exactly what I'm talking about.
So you're talking about how difficult, and my assumption is that this a paper from Athens, as the dust settles, the complexity of writing this mod function is not gonna suck out the advantage of the Shor algorithm, right? It's not gonna produce exponential complexity.
That's
that
right.
right? Okay.
That's correct. But of course, if you actually want to build the computer and actually run it, somebody's got to write down the algorithm that's going to run on the computer. And that's what's in the Greek paper that I just showed you, right? Okay, so somebody has to do all of that work. And so that's exactly what I'm trying to say. The Oracle is really an assumption. It was an assumption, but it was not really an assumption. It was a statement based on principles that had been established by Bennett, that anything that was computable classically with a reversible classical computation could also be computed on a quantum computer in the same order of time steps. Okay, right. So he was using very general principles in order to convince himself that this could actually be done. Right. Okay, that's what I'm trying to say.
And just to cross our H bars here, so and the statement is that doing this modular exponentiation classically on the reversible classical computer is not an exponential overhead.
That's correct. It's polynomial and it's very efficient. It's actually very efficient. And it's, you know, if you want to do this for any reasonable value of n, it's an extremely efficient classical algorithm. It's just that when n has 1,000 binary digits, it slows down just from that exponential growth.
I didn't realize one needed theorem
to show the polynomial growth. Excuse me. Oh, sorry.
So in the book, it's sort of mentioned, if I remember, as a a small subsection earlier on, that's, it develops the notion of classical reversible computation, but then once the notion is developed, the way I understood it all the time is that, once you have the reversible classical computer, you can run it on a quantum computer without entanglement, essentially. You can just run it on product states. Isn't that right? But you're saying that there had to be theorems by Bennett.
There were theorems that were established to show that if you can do it on a reversible classical computer, you could also do it in a quantum computer without exponential speed up. That's correct. All right. Okay. So let's go to the next slide here, because what I want you to understand, what an oracle means to me. That's the article I just showed you. I just gave the reference. Sorry about that. Just go ahead to the next one. Next slide. So try to understand that these people put many millions of taxpayers' dollars into building these extraordinary machines that can talk to individual atoms and individual ions, and then they use them to do addition and multiplication and modular arithmetic. It seems kind of crazy, right? It seems like, okay, we have this incredible new technology and we're trying to train it to count in some very classical way, right? This is sort of what we're trying to do. So I like to make an analogy. Here's my next slide. My next slide is that you go out and you buy yourself a Maserati for the purpose of riding on the sidewalk that runs narrowly around your childhood home. Okay, that's the purpose of Maserati, is to drive on that very narrow sidewalk as you go around your house. So you're going to do with the Maserati exactly what you do with your tricycle. You're just going to look better while you're doing it, and that's what we're doing with our quantum computers. Okay, we're trying to teach our quantum computers to add and subtract and multiply and divide, and all of that is a mess, and all of that goes into these quantum algorithms. But that's what's buried in this whole idea, of just lumping of putting all the dirt under the carpet and calling it an oracle. Okay, that all of that dirt is in there, and it has to be in there to get the machine to run. So let's go to the next slide for a minute, please. Okay. Next slide. All right. So somehow we have. We imagine that we have actually written the information onto our quantum bits. Okay, the oracle has done what it's supposed to do, and it's written our function onto X and Y. Now we're going to do a little simplification, which is not necessary, but which is helpful for educational purposes. It'll show you how the whole thing works. And so it's worth doing. Your book also has a section on this, so you'll see it in your book, okay? What we're going to do is, now that the function is written, we're going to measure the spins in the Y register, in the red second register. Now, we don't have to do that, and I'll get back to Y in a minute here. But for the moment, let's just imagine that we take a measurement of the spins in the Y register. Now, it's quantum mechanics. It's going to be random. We're going to get a random number, Y, on the right-hand side. But it's going to be one of the numbers, 7 to the X mod n. We don't know which one it's going to be. Let's say that it comes out to be 1101. Okay? Let's say that we do the measurement and we get 13. Okay? So we measure the states of the Y we measure the spins along the Z direction of the qubits in the Y register, and we happen to get out the result 1101. What does that imply about the X register? It means the only X values that are going to remain in the X register are the ones that correspond to Y values of 1101. And so our state is going to be reduced by this projection onto a superposition of states of the X register, which are separated by 4 values of 4. So all the other ones are going to be wiped out, okay? Because they have different values of Y. So we're going to be selecting from, so now we're going to be reduced to a periodic superposition of X states, okay? All we did was we made our diffraction grader simpler. Instead of our diffraction grader grading having some complicated structure, now it's just going to be single spikes separated by 4, okay? All right, that's all we've done. So we've simplified the problem by measuring the states of the Y register, okay? And that just makes it easier to do the math in your head and to figure out what's going on. But as I say, measuring the states of the Y register is not necessary. Okay, let's go on to the next slide. So here's what we have. We have in our remaining 8 atoms, and they're in a superposition, a periodic superposition of these states. The values of J are shown over in the left-hand column, 3, 7, 11, 15, 19. These are the corresponding Z components of the spins of the states in those registers. We have a superposition over all these possibilities that are shown in the left-hand column. That's the state of our X register now that we've measured the Y register. So now we have to ask ourselves a question. How are we going to measure the state of the X register? What are we going to do? How many queries of the remaining 8 quantum bits are necessary in order to determine the period of the function? Okay. All we know is that these 8 atoms are in some superposition of states. Somehow we have to figure out by measurements on those atoms what the period is R equal to 4. Next slide, please. These 8 qubits know the period that we're looking for. We wrote the periodic function onto the atoms. What question do we ask of them to find out the answer? How are we going to figure out the period? That's what this is all about. Next slide, please. And that brings us back to the guy in the suit, in the puddle, in the forest, okay? We're back in the land of yes/no questions. We have to ask questions of these 8 atoms to try to figure out which universe we're living in. That's my daughter's middle school story, okay? What questions are we going to ask with these atoms? That's the next slide, please. And the answer to that is the inverse quantum Fourier transform. I think Vadim has already covered that in class. I'm going to do it a little bit differently. Okay. Let's go to the next slide. So the third step, the last step, is eating the food. We prepared the table, we cooked the food, and now we got to eat the food. Here we go. Psi prime is the remaining state of the J register. Okay, those 8 qubits I'm talking about. And there's 2 alternative representations for those qubits here that I'm talking about. One is the J representation that we've been using all along, but another is what a physicist would call the momentum representation, or the K representation. Okay, and they're related by this simple waveform. The amplitude Kj is an oscillatory function. 2 to the t here, I'm sorry, I forgot that notation. 2 to the t is just m, so it's 255. Okay, sorry about that. So all we're going to do to our remaining 8 qubits is we're going to measure the momentum of those qubits, if you will. We're going to project out the Fourier transform, the Fourier component of that state. So that's all we're going to do. And of course, we're going to do it in binary because our qubits are arranged in binary. Okay. So K is actually expressed as K1, K2, K3, K4, K5, K6, K7, K8 in binary notation. Okay. And as I said before, 0 and 1 correspond to spin up and spin down along the z-axis. All right. All right. So we're just going to take the Fourier transform. The questions we're going to ask of those 8 qubits are just given by the Fourier transform. So let's go to the next slide, please. And so the formula in orange is the only one that really matters here. And this is an alternative way of expressing the Fourier transform in binary notation. And you can see that it's a product of 8 factors, 1 for each qubit in the J register. And you see the binary digits of K occur as phase factors in those various components. So if we look at the leftmost qubit of the J register, right? So we're looking at those 8 qubits in the J register. We're looking at the leftmost qubit, and we're going to use that first set of parentheses on the left-hand side in the orange bar. And what if you look at that for a minute, think about it. K sub n is either a 0 or a 1. If K sub n is 0, then that entire exponential is just 1. So you have 0 plus 1. That's a state that's aligned with the positive x-axis. 0 plus 1 is a spin pointing along the positive x direction. If, on the other hand, K sub n is 1, then 0.1 corresponds to a half in binary notation. And so that's e to the minus I pi, which is minus 1. And so you have 0 minus 1, which is a state whose spin is along the minus x direction. So that left-hand parentheses is asking the question, is this spin, remember when we prepared the spin along the positive x direction, all the spins in the x register were along, in the J register were along the positive x direction. Now this left-hand parentheses is asking the question, is that spin still along the positive x direction, or is it now along the negative x direction? So it's just measuring the spin along the x direction. And from that measurement, it determines the value of K sub n. And K sub n, here, that would be K sub 8, okay? So K sub 8 is the first binary digit of K. So measuring the last qubit along the J register gives us the first digit of K. And then if you look at the second set of parentheses, you see that we have to, once we know that value of K sub n, then we can figure out what measurement to make on the second qubit. If k sub n was 0, then that whole exponential is 0, and the exponential reduces to 1, and again we have 0 plus 1, and so again we're going to measure that qubit, that second qubit, along the x direction. However, if k sub n was 1, then we have to go back and look again. If k sub n were 1, then the value of kn minus 1 matters. Actually, I wrote that incorrectly. There's a typo there. It should be kn times kn minus 1, not kn minus 1 times kn. Okay, all right. Okay, because that is going to bring in a value of a fourth, which is going to be pi over 2. So that's going to correspond to a spin along the positive y direction. And so in the first set of parentheses, we measure the spin along the x direction. In the second set of parentheses, we measure the spin either along the x direction or along the y direction, depending upon the result of the first measurement. And you keep doing that all the way to get to the end. So the next slide has the algorithm for the Fourier transform written in a rather different way. We're going to set a detector in the xy plane of our spin. The phase of the detector, the azimuthal angle of the detector, is going to be set at 0. That is, it's going to be aligned with the positive x-axis. We're going to measure that qubit. Depending upon the result of that measurement, we're going to change the position of our detector. And then we're going to keep doing that. The next slide shows you how you set your detector. We start out with the qubit, with the first qubit there on the left, with the azimuthal angle equal to 0. Depending upon the result of that measurement, we either move along the orange line 0, or we move along the blue line 1, and we change the azimuthal angle of our detector. Depending upon the outcome of the measurement of the second qubit, we move to a different angle, and a different angle, and a different angle. Every time we measure a qubit, we change the orientation of our detector. I got tired of writing after 5 because I was getting tired of drawing all the lines, okay? But you can see how it goes. You can also see that in order to measure this k, you're going to have to be able to orient that spin detector in the azimuthal plane with increasing fidelity as you move around the circle. All right, you're going to, as you move to higher and higher numbers of qubits. By the time you get to the 8th qubit, the difference in orientation of the detector is a very fine gradation. So let's go on to the next slide, and now you'll see how it works. Here's our state. We're going to ask 8 questions. And from 8 questions, we're going to find out the value of k. And that's the key. This is why the Fourier transform is fast. You ask 1 question of each atom, and you're done. Next slide. Now, if you actually look at the possible values on the left-hand side, you'll see something very curious. If you eliminate the right 2-hand columns, you see the right 2-hand columns are all 1, right? Because this is a periodic function. So those correspond to 2 spin down. So the last 2 spins are spin down along the z direction. But get rid of those in your head and just think about the rest of the other 6. The other 6 are, the first one is 0, 0, 0, 0, 0, 0. The next one is 0, 0, 0, 0, 0, 1. The next one is the binary representation of 2. The next one is the binary representation of 3. The next one is the binary representation of 4. So you can see that the first 6 spins are still all oriented along the positive x direction, just like they were when we started. The only thing that our function did was it moved the last 2 qubits from the positive x direction into the negative z direction. That's the only thing that it did. I hope you can see that. You have to look at the numbers in the columns on the left-hand side. They're just the binary representations of 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 7, like that. Okay. So that is, we know how to make that state. It's just the superposition of X values, or I mean, and it's just the product of spin in the X direction values for each of the qubits. That's how we set the table at the beginning. The only thing that has changed is the last two columns, which are now spin down in the Z direction. That gives you the numbers 3, 7, 11, 15, 19, like that. So now we know how to calculate K. So let's go down to the next slide. So we measure the leftmost qubit along the positive X direction, and it's still in the positive X direction, and we get a value 0. And then we go to the next qubit. We leave, because the first qubit answer was 0, we leave the detector along the X-axis. And we measure the second qubit, and it's also 0. And we're going to do that for the third and the fourth and the fifth and the sixth. Okay. So we're going to get 0, 0, 0, 0, 0, 0, and now we just have two things we don't know. Let's go to the next slide, please. Now, when we get to the 7th qubit there, okay, the second one from the right, now we're going to, our detector is still in the X direction, right? We're still looking for spin in the X direction. The thing is spinning down in the Z direction. So half the time we're going to get a 0, and half the time we're going to get a 1. Okay. So now you see in the second decimal place to the left in K, you get either a 0 or a 1. If it's a 0, then you leave the detector in the X direction and you go on and measure the last qubit. And the last qubit is pointing down in the Z direction. So again, you get a 0 or a 1, okay? And so that gives you the first column, and it gives you the third column. I'm sorry, the first row and the third row in K, right? However, if the 7th K qubit there, right, if that one came out to be 1, then we have to move our detector to the Y direction, and we measure the spin in the Y direction. And since it's spinning down in the Z direction, we're going to get a 0 or a 1. And that gives the other two possibilities. And now you look at the values of K, and there's 0, 64, 128, and 192. Next slide, please. "25% when we do of the time when we do this measurement, we're going to get 0. That's like catching a photon that went straight through our diffraction grating. We don't get any information from that. It's useless, right? We can't measure the diffraction grating if we're only measuring photons along the axis. So 25% of the time, we get a result that's useless, and we have to go back and start over. But in any of the other three cases, all of which happen with probability 25%, we get a value of K, which is non-zero. And remember, and I wrote this many slides ago, the relationship between the periodicity and K is the value of M, which was 256 divided by K, and N is the order, right? So we either have R over N, right? So if I take 256 divided by K, we either have R over N equal infinity if you're in the 0th peak, or we have R over N equal 4, 4 over 2, or 4 over 3. And from those measurements, you can infer the periodicity R. Just like the question I asked you at the start of the day. Next slide, please. Okay. So the reduction, the reason we were able to do that by hand without really thinking much, just playing around, was because we first measured the Y register. And by measuring the Y register, we generated a periodic function of X, of the J register, right? But what if we don't first peek at the Y register. I told you it wasn't necessary. Okay, I told you we don't have to measure the Y register at all. That's not obvious. So why should taking the Fourier transform give us the right result, irrespective of whether or not we measure the Y register? This is also described in your book, although rather differently than I'm doing it here. The key is to try to rewrite the state of the Y register in terms of the eigenstates of the A operator. You see, psi is really just a to the j, the A operator to the jth power multiplied by the state 1, right? And that's what we're trying to do here, right? A to the j times the state 1. If we write that out and we take the Fourier transform, here's our Fourier transform coefficient, we have a to the j times the state 1. Now, if I sum that over all the j's, that's just a geometric series. And I know how to sum a geometric series. This is what you get, right? Okay. Next slide, please. So the remaining state of the Y register, if we measure the momentum on the J register, the remaining state on the Y register can be written like this. And now I'm going to express that in terms of the eigenstates of A. Now A is a unitary operator, and a to the rth power is equal to 1. That means the eigenvalues of a to the r of A are roots of unity. Okay, this has to be the eigenvalue just based on the fact that A is unitary and that a to the r is 1. So these are the eigenvalues. And the number of eigenvalues is determined by the periodicity of the function. So we can write the state 1 as a superposition of the eigenstates of the A operator. Now, because R is less than the number of states, n, there's going to be some degeneracy in these values. So I'm writing this sum in two ways. I have sum L equals 0 to R minus 1. That's the number of distinct eigenvalues. Lambda is just a convenient label for states that are degenerate and have the same value of L. And I can show you that we can reduce that to a single sum. So the state 1 can be represented as a sum over, in this case, 4 distinct eigenstates of the A operator. And I put that in as extra slides 62 to 65 in my notes because it's laborious and I didn't want to do it. Your book uses a different argument to come up with this equation, okay? But this is a more general proof, okay? And the idea here is just that you can always choose, since you have degenerate states, you can always superimpose them in such a way that only one of them is aligned with with this direction of Hilbert space. That's really all it amounts to. So you get rid of the sum over lambda, okay? Because all the other ones are orthogonal to 1, all right? So that's basically it. And then you can choose the remaining phase of that 1 in such a way that the coefficient here is unity and they're uniform. And so this is, but I proved it for you in this particular case in slides 62 to 65. If we just insert that for 1 here, we now have eigenstates of A, and so we can evaluate this thing. And so if we measure using the Fourier transform, the Fourier transform of the J register, what remains in the Y register is simply this. It's a sum over 4 values of L, where L is the eigenvalue of the A register that goes from 0 to R minus 1. And you see that the coefficient is the sinc function, sine over sine, okay? So this function is strongly peaked when K is Lm over R. So if you measure the value of K as we did before, this is the same condition which we just used a moment ago for determining the values of R, okay? This is exactly the same criterion. So it doesn't matter if we measure the Y register or not, we get the same answer, okay? That's what I'm trying to tell you. Now, next slide, please. That factor, sine over sine, is the factor that I described earlier when I'm talking about diffraction from a grating, okay? This is why I put so much emphasis on this simple interference phenomenon when we started the talk, okay? You have to, it's very hard to put yourself in Peter Shor's shoes. He was doing this in 1994. He didn't have a lot of tools at his disposal. He had some very general principles. And he understood quantum mechanics. And he knew that he was trying to determine the period of a function. And he knew that he was going to try to write that function onto some quantum bits to see if he couldn't find a simple way of doing this. And in order to do it, he wanted to reduce he wanted to use the fluctuations to process the information as efficiently as he possibly could. And that's what this is all about. How am I doing on time, Vadim?
It depends. I mean, are we doing 2 hours? I mean,
Well, what time is it
usually we have
now?
1 hour. You're over time the regular lecture, which is 1 hour, but that's fine. You're almost
Okay,
finished.
let me just take a few more minutes because I haven't got to dessert yet. So let's go to the next slide. Okay, okay. You know, the troublesome part of all of this is that oracle. Okay, because that's where all the dirt is buried. Okay, that's the hard part. That's the hard work. It's the bottleneck. It's the tough part of writing the codes. Okay, and it's very difficult. And it's bothersome because we spent millions of dollars on these machines, and people all over the country, probably the U.S. is investing billions of dollars into this enterprise by now, building these very fancy machines. And yet we find that in order to use them, we have to do these elementary operations that our classical computers are already so good at doing. And remember that the fidelities required to perform these operations have to be very good. And in fact, I haven't talked about fault tolerance. That I'm sure comes later in the semester, but how do you correct for errors, right? What do you do when you get errors? And how do you fix the system? In some ways, we know how to correct for errors. You try to build redundancy back into this, but you can't build redundancy back in such a way that you destroy the fluctuations, because the fluctuations are what you're using to calculate the thing in the first place. So you have kind of intrinsic difficulty in trying to figure out how to do these things in an efficient way, but also in a fault tolerant way. So I've been thinking a lot about this, and I just have a silly thought that I want to put in your head, okay? And it's kind of an exercise for the student, but let's go to the next slide. So my solution to this problem is what I like to call Little Orphan Annie's self-destructing quantum decoder array. Okay, that's my solution. It's a little bit crazy. The whole problem that we have is the problem with the Y register. Remember, there was the extra state conundrum there, right? The problem with the extra states that make, right? That's complicating. There's also the fact that when you're doing the computation, you have these extra qubits you have to add in just to carry over the results, right? I mean, you always have to have more workspace to do the work in, right, that you need. And that adds extra complexity to the system. And all of the difficult operations that we're performing with the oracle are operations on the Y register. They're very complicated operations. And so I thought to myself, gee, why do we need to have such a complicated thing? Let's get rid of the qubits for the Y register. Let's find a simpler quantum system for the Y register, one that has already the properties that we need. So imagine that we had a quantum system where the modularity became obvious. Imagine that we had n atoms arranged in a circle, and we can plop an extra electron onto one of those n atoms. Okay? Now that's a system, you know, the electron can exist at any one of the points at the tip of any one of those arrows in the picture, right? So the electron has exactly the right number of states, right? And it's intrinsically cyclic, so we don't have to do any modular arithmetic at all. We can just get rid of the modular arithmetic. We just use this electron. All we have to do is multiply by powers of 7 and let the thing go around as many times as it wants to go around. And we can do all the math without ever doing any modular or anything. That would be a very simple quantum system. Unfortunately, we have, you know, n's with, you know, 1,000 binary digits, okay? So it's not easy to physically construct such a thing. But of course, it's not easy to physically construct Shor's quantum computer either, okay? But let's imagine that we had such a thing. In fact, we do have such a thing, and it's very simple. Next slide, please. We have a single qubit. We have an azimuthal plane of a single qubit, which is a circle. We can orient the spin of that one qubit along any angle phi in the azimuthal plane we want. And we can define n states very easily for the orientation of that qubit. Next slide, please. So why don't we do this? Why don't we have, for our quantum computer, an X register that has 8 spins along the X direction, and a Y register which is in a single qubit. And initially, that Y register is going to be pointed along a direction 1/15th way around the circle, the azimuthal circle. That's represented by that state in red on the first line, okay? And then our operation U is going to rotate that spin of that extra particle by an amount of 7 to the jth power over 15 times 2 pi. Right? So it's going to rotate it around the circle. The modular arithmetic is done by the phase. We don't need to worry about modular mathematics anymore. Now I know what you're going to say. You're going to say, yeah, but those states are not orthogonal, right? Those states of that extra spin are not independent states. They're not orthogonal to one another. But it doesn't matter because we're not going to measure the Y register, are we? If we never measured the Y register, what difference does it make? We just need something that's periodic with the correct period. That's all we need, okay? In fact, this is why I call it the self-destructing. Where was it? The Little Orphan Annie's self-destructing decoder ring, right? Okay, now that we've thought about it, we don't need it anymore. We're gonna just get rid of it entirely, okay? We're just gonna keep the phase. We don't care about the 0 and the 1. We're just gonna keep the phase, okay? We're gonna have our initial state of 8 atoms spinning along the x-axis. And then we're going to hit them with a U, and the U is just going to give a phase. All we're going to do is modulate the J register with a phase that has the desired period. That's all we're going to do. And then we're going to take the Fourier transform. Why won't that give us R? What kind of unitary operator U would do that? And what kind of gates would you use to make it happen? Is this a Maserati or is it a tricycle? What do you need to make that work? That's a question for the student. Okay, think about that. Think about whether we need the second register at all, because we never measure it. Last page, please. We're done. Okay. You'll see that down below down there, I have the extra slides that I promised on how to diagonalize the A operator. Okay, all right? Okay, that's down there at the end. And I provided Vadim with a copy of my slides, which he can share with you. Okay. And that's my talk for today.
Thank you. Any questions? So if I understand, you're proposing a tweak to the Shor algorithm to what I guess my guess would be that extra single qubit, the self-destructing component, is actually highly susceptible to noise, much more susceptible than the previous guys. How does one do error correction on? Does one need to worry about that?
Well, so let's go up a slide here and just talk about that for a minute. Okay, so we're not going to actually use an extra qubit, right? We're just going to eliminate it completely, right? It's self-destructive. We're just going to have a set of qubits on our representing our J axis, and we're going to modulate them in some way. So we're going to generate a unitary transformation which modulates the states along the J axis with a complex oscillating phase here, right? Okay, and with an oscillatory phase that has the correct period. So there is no such qubit, but recognize, you know, one of the reasons that I don't. One of the reasons that I formulated this whole discussion the way I did is because it indicates to you physically how difficult this whole thing is to do, even if you do the canonical thing the way Shor did it, okay? The Fourier transform, we normally, you see, I did the Fourier transform by taking my detectors and rotating them in the XY plane. Now, no physicist is going to take spin detectors and rotate them in the XY plane. Okay, we're not going to do that. What we're going to do is we're going to keep the detectors fixed, and we're going to rotate the states and make the detections that way. Okay, so we always measure things along the Z direction, and we rotate the states in order to make that happen. That's the quantum Fourier transform algorithm that Vadim taught you. Everything's measured along the Z axis. Right? The spins are always measured along the Z axis in the standard Fourier transform. Because you think that way, and because you do it that way, you lose the perspective that what you're really doing is asking one question of every qubit. Okay? Because you have to rotate the qubit to put it in a position to detect it. Okay, all right? Okay. So the whole reason I structured the Fourier transform discussion that way is so that you can see how difficult it is to do what Shor's asking us to do. You have to be able to resolve, or not, resolve is not the right word because we're not resolving a signal, but you have to be able to physically rotate that detector with a fidelity which is astonishing. The angular change you're talking about is 1/2 to the nth power, where, right? Okay, right. Okay. Where n has 1,000 decimal digits.
Right.
That's far better than we can point any telescope that's ever been invented, okay? By many orders of magnitude. Okay? right? But if you write it in terms of gates, with everything measured along the z direction, it just doesn't dawn on you that that's what you're that's what you're up against. Okay, you think all I have to do is get a certain fidelity in my gate operations, right? And I should be able to do that. It's just a number, right? But then when you actually start to think about it in these geometric terms, it really becomes real to you and it hits you in the gut and you say, oh my God, am I really going to ever be able to measure anything to that level of precision in order to really see and really make this work? That's what you're up against, okay? And you're up against it even in the standard Shor formulation, and you're up against it here too, because that 15 is going to go away and it's going to be a number n, right? Okay, right? And n is going to have 1,000 decimal digits, right? So you're going to have tiny little, you're going to have to do a very high finesse phase modulation of your J values in order to dress the state in this way. And you're going to have to do it with two-body operations that link these various qubits together, okay? Because obviously they have to talk to each other in order to do this, okay? And that's why it's tricky. And what's really tricky about this last formula down the bottom, I don't want to give you the answer because it's sort of an exercise for the student, but J, if you write J down in terms of its binary digits, what you see there is that the phase is a product of factors from all of the various qubits. Okay, it's not a sum of factors from the various qubits. That would be trivial and easy to do. It's a product of factors from all the individual qubits. So now you have to figure out some way of using two gate operations to manufacture a phase, which is a product of all the phase, a product of all the J's of all the spins in the system. I'm afraid it's going to stop looking like it's going to start looking like a Maserati pretty quickly. Okay, that's okay, right? You see what I'm saying? Okay, so that, I don't know if that answers your question, Vadim.
But in a way, yeah, because by packaging, yeah, I guess I haven't quite wrapped my head around this sort of a modification, but it seems to me by packaging that Y register into a single qubit, you're essentially somehow using the continuity of quantum, the quantum phase there to essentially encode an exponential amount of information, and that seems anyway, yeah, I just want to think about it, how why is that a good idea? That's not obvious to me.
Well, I mean, the point is that it's a simple exercise for the student to show that when you take the Fourier transform of the last line, you can calculate R right away. Okay,
right.
So this works. There's no doubt about it. The question is, what is U? Okay, what kind of U would you need? Right. So again, we're back to the Maserati tricycle question. What kind of U do you need? What kind of oracle are you going to have to invent that can produce that kind of phase modulation of the J-axis, right? And that's the tricky bit. Okay.
Have you reached out to the authors of the 2013 paper in Greece to see if they can?
No, there's a lot of those papers. So I showed you one of them.
Right.
While I was at NSF, one of my colleagues there, the one who was from the SAIS directorate, computational directorate, he running that program, he found an even better and faster way to do the modular exponentiation. Published a paper on it, which is not the paper I showed you. It's actually a little bit faster than their algorithm. And then IBM hired him, so he went straight to IBM. So now he's doing quantum programming for IBM, right? And so there's a lot of papers like that. I chose that one because it has a lot of very fancy diagrams showing all the various steps to creating an algorithm for calculating that modular exponential.
All right.
Okay.
I think we should probably stop.
Well, I hope it was helpful to the students. I hope they can.
I hope so.
Again, I know when you're learning something, sometimes it's best to do it just one way. So I was a little hesitant to present anything which is slightly different from the textbook, because sometimes the first time you learn it, you want to just have one way of approaching it. Well, so I was a little reluctant to do it this way, but hopefully you'll find it instructive, and it'll cause you to question some of the things you're reading in your textbook. So good luck with that. Okay.
All right.
All right. Thank you, everybody. Nice to meet
Thanks
you.
very much.
Yep. You're welcome. Bye-bye.
Bye.
Take care.
Bye.